Alright, welcome back everybody. XPhys guy here again. Today we're going to cover the cardiac cycle. Now this, as I have it drawn up on the board, is usually not covered in undergraduate studies in such a way. We usually just leave it in that the heart has a systole period and a diastole period. In other words, an ejection period and a filling period. And we usually just kind of go by that. What I'm going to do here is I'm going to try to explain in some easy terms what exactly goes on in one cardiac cycle. So in other words, in one heartbeat, if you will. Now these are graphs that you're not really going to see outside of textbooks. And chances are, even when you're doing exercise tests, even laboratory exercise tests, you're not going to be doing much with these graphs on here. They're a little bit advanced beyond the XPhys exercise physiologist in measurement, but in application and in physiology, it is important to get a visual of what really is going on with the heart chambers and the heart valves during one cardiac cycle. So again, we're just sticking to one cardiac cycle as we are doing the graph. The first part that I actually want you to look at, and I'm going to just move the camera here because I think I'm cutting off a little bit on the top. I am. Okay, so the first part, I actually want to look at this chart over here. So this chart is going to have pressure on the y-axis. So that's pressure up on the y-axis, and on the x-axis you'll have time as it is. And when we're looking at time in a cardiac cycle, we're talking about fractions of a second. So if we look at the pressure, we'll see that we usually talk about the cycle as beginning with ventricular filling. So in ventricular filling, what's going to happen is our aortic valves, so our atrioventricular valves, tricuspid and mitral valves will be open, allowing for blood to fill the ventricles. Okay, so they're allowing for blood to fill the ventricles because remember, the tricuspid and mitral valves go into the right and left ventricles respectively. So the valves are open, blood is coming in. Now what's going to happen is mitral valve is going to close right at this point. So if you imagine sort of after a P wave on an EKG tracing and during the QRS complex, the mitral valves have closed and we go into this period called the isovolumic contraction period. Now during this isovolumic contraction period, which I'll also show you on this graph as well, all four of the valves are closed. And what's happening is the heart is basically squeezing in on itself, and it's increasing pressure without any more volume coming in, so without any more blood coming in. And it does this up to a point where it exceeds the pressure that's basically on the other side of the aortic valve, if you will. So once the pressure in the ventricle reaches that of the aorta, then the semilunar valves, the aortic and the pulmonary, will open. Once that happens, we can get ejection. So aortic valves open, we have ejection of blood. So we have ejection of blood, and then we're going to start relaxing. Then we're going to get into this isovolumic relaxation period where the aortic valves close, and this again is resulting in all four valves being closed. So anytime we are isovolumic, all four valves are closed. It'll come down to pressure at a certain point, mitral valve will open again, and we can restart the cardiac cycle. So if we look at it on, now this is a very common, what is called ventricular pressure volume loop. So if we look at a ventricular pressure volume loop, we have volume on the x-axis and pressure on the y-axis. Now this is going to be a helpful tool for maybe some undergraduate students, but definitely graduate students as they get into looking at things like stroke volume, afterloads, preloads, things like that. And if those terms are unfamiliar, Preload is the amount of blood that's returned to the heart during diastole. So once the heart is finished filling, that's your preload. And your afterload is the pressure that opposes the ejection of blood. So hopefully those make sense. But back to the loop. So what we are looking at on this loop, ventricular filling, right? So we had ventricular filling over here, where our tricuspid and mitral valves are open. We have filling, so volume is going to increase while pressure stays low. We're going to get to point B. After we are filled, and we're at B in stage 2, that's when we're in our isovolumic contraction, where all valves are closed. So again, the heart is squeezing in on itself at this point, creating a buildup of pressure until a certain point that pressure is at or beyond the aorta. Now our aortic valves and pulmonary valves will open, causing or resulting in ejection. We'll get to point D. All valves close up. This causes ventricular pressure to drop, and then we will go and we will fill up with volume again. So it's a very complex process, but once you look at it a few times and you study it a few times, it becomes easier to understand. And you can think of on the pressure volume loop chart here, you can think of it as being, if you remember the other vocab words we talked about, isovolumic contraction. Right up here at point C, this is the end diastolic volume, right? Because during the filling phase, this would basically be diastole right here, where we are filling up, you're going to get to a certain volume. This is end diastolic volume, the amount of blood that is in the ventricles after the filling phase. Over here at step A, this would be end, or D, it doesn't matter, you're still in the same volume spot. This is end systolic volume. So this is the amount of blood that is left in the ventricles after systole. So to get stroke volume, you would basically take your end diastolic volume here, and you would subtract your end systolic volume. And that's how you're going to get your stroke volume, which is the amount of blood that's ejected from the left ventricle per cardiac cycle. So now we can look at it as one cardiac cycle, one heartbeat, instead of just saying, well, somebody has a resting heartbeat of 60 beats per minute. That means this entire cycle is happening 60 times in 1 minute. And here we can really see the benefit of having a lower resting heart rate from something like training, not from something that's a congenital defect or some other venue. Because you can have low resting heart rates and it cannot be good. But the isovolumic contraction, anytime you're isovolumic, that's a great amount of pressure that the heart is put under. It's a lot of work. So it's very beneficial if we can have isovolumic contraction occur as minimal times as possible. So yes, this area inside the pressure volume loop basically represents myocardial work, or the amount of stress that the heart is put under. And during exercise, yes, this widens. But from exercise, we lower resting heart rates, we lower the number of times the isovolumic contraction happens. And how do we do, what's the mechanism for that? The mechanism is that with training, your heart is going to be able to fill a greater amount of blood, and through something called the Frank-Starling Mechanism, which I will cover in another video, it basically says the more you fill, the more will be ejected. And there are some upper limits to that, but I'm not going to get into that because that's some real cell histology and physiology that we don't really need to cover. But basic principle, if you can fill the chamber, the ventricle, with more blood, then you can eject more blood. It's simply like a rubber band effect. If you stretch a rubber band more, it'll spring right back with more force. So same thing that's happening here. We fill the ventricle more and we stretch it, and just as an elastic property of the myocardium, it will eject more, let alone the fact that you can increase muscle mass and create stronger contractions that way. But anyway, that's ranting and pontification. Come back to the original cardiac cycle. You have ventricular filling, which occurs here, right here. And then you have your isovolumic contraction. All valves are closed. Here, pressure is increasing up to a certain point. Okay? Then the aortic and pulmonic valves open, causing ejection. All right? Pressure will drop. Okay? All the valves will close for isovolumic relaxation. Pressure will go down, 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 down. And then when the pressure is lower in the ventricles than it is in the aorta, that's what causes that mitral valve to open. I know I didn't say that before. Well, how do we get, it's a loop. So how does this occur over here? The pressure drops enough so that the pressure inside the ventricles is less than that in the atria. And that's one of the most important physiological concepts we can have, is something called a gradient, a pressure gradient. The pressure is always going to want to move from an area of high to low. Always, always, always. Which is why isovolumic contraction is so taxing on us, because we're trying to build pressure. I know this was a little bit of a difficult concept today, and I kind of was all over the place. As always, I hope that this was informative and maybe helps you kind of understand the cardiac cycle with these two charts a little better. These are common charts that you will see in exercise physiology books and cardiovascular physiology books. If it didn't make sense, or you want me to go in a little further about what's happening in the cardiac cycle, as always, leave a comment down in the sections, and I'll be happy to look into it. All right, bye.